But one of the points that you've consistently made that I've always found interesting is that seemingly complicated machine learning capabilities are ultimately based on relatively simple math. Say relatively simple for you than me, but what are some examples of the mathematical foundations that can date back decades, if not centuries, that ultimately make up modern ML applications?
Yeah, it's such an interesting question, and so I am now quite a bit older than you, Rad, in my 60s, sort of, and so of course I never studied anything about AI or ML at school, and all of this has come along, in my lifetime. But of course, as a mathematician, the first thing I had to do was delve into the maths and think, what kind of amazing, incredible new maths has been developed to power intelligence? I mean, intelligence, it's just something mind-boggling. And I looked at some of the first early algorithms, and I'm pouring through all the paperwork, and I'm seeing multiplications and additions, and I'm thinking, oh, come on, guys, where's the math? It's got to be more than that. And it really isn't. It's really something incredibly simple. But what kind of makes the difference is the fact that we've always been able to do simple calculations from early Egyptian times, or probably before. Simple mathematics existed. But it was all done in our brains for very simple things. Getting the change right in the bazaar, buying things. But suddenly we've got these computers that can do 1 million calculations a second, 1,000 million calculations a second. And what's been so interesting is if you just take really basic math, but repeat it so that it's no effort to just do it a lot, that's when incredible things happen.
Like your calculator example.
My calculator example, no, that wasn't very millions of, I should have brought in a calculator, but yeah. Yes, it was one of the first things I remember when I was at school. In fact, when I was about 8 years old, I had a mechanical calculator. And at the same time, my dad gave me his slide rule. Remember the old sort of slide rules? But electronic calculators came out when I was a teenager. And I was about 13 when I got my first scientific Casio. And I was fascinated by that thing. And I'd often sit in lessons just bored and jab at the buttons. But there was one button that you press, and if you keep pressing it, it looks really interesting on the calculator, and that button's the cosine button. And as you're pressing it, you're seeing numbers on the screen, and they're constantly flicking and changing and changing and changing. But after probably 20 minutes of French verbs, when you're really bored, you realise that number stopped moving. It's suddenly the same number. And I didn't know it back then because none of these terms existed. But me jabbing the cosine button was actually an example of machine learning. The calculator had learned the solution of a simple equation that evolved a cosine. And I did it with a machine. So yeah, I mean, machine learning goes back, for a long, long way.
Absolutely. Speaking of going back a long way in high school math, see, you have a couple textbooks here, one focused on a vectorial approach. Can you tell me a little bit about vectors and why they're so important when you think about modern applications like large language models, but also how far back their origins ultimately go, to Newton in the 1600s?
So I was, now I know this is going to sound really bad, but I was actually very fond of this book when I was at school. This was my high school textbook, and I had a particular, I was in the set that they called double maths. We had pure mathematics.
Sounds like my worst nightmare.
Yeah, exactly, it would be. I mean, we were, of course, all the kind of sporty people at school loved the double maths set because, of course, we were really hip and cool, and we were the real kind of nerds of the school. So
that's brilliant.
My nerdy background goes back a long way.
It paid off.
But actually, we had a brilliant young teacher. He was straight out of university, Mr. Ironside, fantastic name. And this was the book. And the reason why I loved it, and you can see it here on the title, Modern Mechanics, a Vectorial Approach. It was a different way of looking at mechanics. And mechanics is just physical stuff. So this book looks into things like pendulums, springs and forces on cars. It will teach you the mathematics of, let's say, a missile, a cannonball being thrown out of a cannon, the way the planets attract each other and why they move into ellipses. It all comes out of here. And it all uses a simple mathematical idea called a vector. And a vector is just a list of numbers. A number, we're all used to numbers, 1, -2, 3.1. But in a vector, you just collect them together in a list. But what's interesting to me was all of the vectors in this book, most of them are two-dimensional. They have two numbers. And for some of the really more complicated problems, we might have 3 numbers. And that was the limit of the size of a vector. But when you learn to start working with vectors, there are simple mathematical tools that do things like the size of a vector. Or there's the concept of distance, which we can come back onto. So, I mean, here's an example. Let's imagine I take a map and I put my finger on, let's say, the centre of London. I can draw a line out to, say, Bristol, and that line is a vector. And this is a concept that humans have. It has a distance. Bristol is actually nearer than Edinburgh. But there's also a concept of the direction. Bristol is not in the same direction as Edinburgh. But there's a concept that we can measure the distance between Bristol and Edinburgh. So with two vectors, there's this idea of, distance and direction and size, and that's sort of what they do. What I found amazing when I first started studying machine learning is people just thought, well, if we've got a computer to do all the hard thought, what if we don't limit ourselves to 2 numbers or 3 numbers? Let's go crazy. Let's have a 10-number vector. And then, things start behaving in a quite weird, in a different way. But immediately people just thought, well, let's try a 500-dimensional vector, and let's think about a 10,000-dimensional vector. You can throw away the rules and just say to your computer, right, just do it this way. But if you think, I think why that was hard for humans is my map example. The vector tells us where a place is on the map. If we added another dimension, it might tell us where an aeroplane is, and the other dimension is the height. So we could have two aeroplanes actually over the same town, but they're at different heights. And a human can visualize what that means because we live in a 3-dimensional universe. But if we tried to visualize aeroplanes flying around in a 4-dimensional universe, well, we could probably do that because you might consider time as a dimension. But then a 500-dimensional universe, a 1,000-dimensional universe, what does that mean? The computer doesn't care. It just sees, it's either a list of 3 numbers or it's a list of 1,000 numbers. It makes no difference to the computer. So yeah, I think vectors were so interesting, and they absolutely underpin everything.
For sure. And how do they function if you think about, going from the 1600s and some of the research there to today with large language models? Because we hear a lot about this notion of vector embeddings, or the numerical representation of numbers, sort of translating different data formats, whether text or audio or video, into a language that an algorithm can understand. Like, how have they sort of advanced over the centuries? Well,
I think it's interesting because I would love to be able to go back in time or bring, say, an Isaac Newton or someone to show them what we're doing, because I guarantee you Isaac Newton would absolutely understand every part of the mathematics in what we do with vectors. The mathematics has not changed. the change, as I said, was this sort of leap that, he would be looking at two-dimensional or three-dimensional things because people were modeling the physical planet we live in. We want to model how cars will drive or how missiles will fly or whatever it might be. And of course, what we're doing with nowadays is, we're doing something, far more complicated. So that's a big change, is this whole sort of idea of scale. But the actual math hasn't changed. But another reason why I would love to bring someone like Newton here is he also did a lot of work around my calculator example. The calculator was solving one equation. It can solve a basic equation around cosines, and that's a fluke. But what Newton did was he said, well, how can we develop a technique for solving loads of different equations? And so loads of different models. And he invented mechanisms to do that. And those mechanisms are in machine learning. So he, for example, he had what's called Newton's iterative formula, and it's a way that using repeated numbers on a calculator you can solve equations. And you start with a guess, and you just keep calculating and calculating and calculating until you get an answer. It's actually the way that calculators do things like calculate square roots. Although interesting, there's a guy called Heron who was around in about 100 years before Christ.
It's going way back.
Well, it's going way back. And he invented the first kind of, he had a way of working out square roots using kind of a mathematical process, which I'm going to do a video on actually sometime soon.
Brilliant.
Because I find it, really, really fascinating. So Newton has got this way of solving these equations. And what do we do with machine learning? We set up say a neural network, and we just give it we put random numbers in there, and we say this is our best guess. It's not a good guess at all. But when we're doing training of machine learned models, those models start to get slightly better and slightly better and slightly better. The more data we put in, and the more times we repeat it, and they're actually getting better using a concept called the gradient. And that's exactly the same concept that was used in the 1600s by Newton when he developed a way of solving simple two-dimensional problems. So he would absolutely understand what we're doing. It's just he would never have been able to do that kind of calculation across a 10,000 dimensional universe.
For sure. I love it. And I guess where we're at now is, vector databases and organizations utilizing those that have, to your point, tens of thousands of dimensions. And within that, is it the ability to create these sort of notions of embeddings that allow algorithms to search and find information that's similar to each other? So you mentioned like the Paris example. Paris in a high dimensional vector space would align quite closely, I'd imagine, to the word France, if you will.
Again, that was what I find. I do truly find some of the applications around machine learning and AI to be quite astonishing, what they achieve with the simplest of ideas. And the first sort of word of embeddings, they would train a model by taking a set of words. I mean, I've got some words in here. We shall from this point refer to the magnitude of a vector. And all they would do was take every word and look and see what word comes close to it. And they would try and predict what the next word is. Just simply the next word. And the model would train itself to just make that prediction better and better and better. But then over millions of words, patterns start to emerge. So for example, after the word pet, it'll see a lot of cat. And that means that pet is very close to cat. Now, after the word pet, it would see a lot of dog. So pet has to be close to dog. Now, there weren't many texts that have cat dog or dog cat close to each other. So it wouldn't normally have found that those concepts are related. But because pet is common to them both, if pet is close to cat and it's close to dog, cat and dog have to be close. So the model has got this idea of a sort of a concept. A cat and a dog, they are pets. And rabbits might end up in there, or budgerigars, or whatever it might be. And so all of those words are assigned a vector. But the way the maths works, and it was eerily powerful for such a simple process and such a simple concept, that we're simply, by just throwing masses of text at this model and training it, we convert individual words into a vector, a list of, let's say, 500 numbers. And as I said to you, our idea of, how close is Bristol to Edinburgh, there's a concept of closeness on these numbers. And
just like a map.
Just like a map. But this map is not on a flat map. It's not even on a globe. It's on a universe that is 500-dimensional universe. So yeah, it's freaky to try and see it in your mind. The trick is don't just go with the fact that these things can be close. And then these embeddings really understood language to the point that, and there's lots of examples on YouTube of people who do this. You pick a vector for, let's say, man, and if you subtract the vector for woman, you get a vector that it doesn't mean anything in itself, but it's a vector that explains gender. It explains the difference between what separates a man from a woman. And eerily, if you tried the same thing with king and queen, or boy and girl, you get a very similar vector, because these numbers have somehow understood meaning. And then these are very well known now. There's examples of people who will say on their computer, they'll take what's Paris minus France plus England. The answer is some vector. And when you say, well, what's the nearest vector to that number? Well, it will be London. Because it has understood that Paris and London are capitals. And it has understood that there is a connection. And of course, because when it was reading texts, it would see sentences, would say things like, the capital of Paris is, of France is Paris. That France and Paris are close. London and England are close. And so it will start to make the connections. Fascinating.
Absolutely. Really mobilizing information at a different scale than we've ever seen before. Now, you mentioned the concept earlier of neural networks, and wanted to go back to that a little bit. But before sort of going through what is a neural network in terms of the machinery of it, what is a neuron? Because that came around, I think, in like the early 40s, the first computational neurons. So can you describe that a little bit in terms of why it's so important in the makeup of the application of neural networks?
Yeah, I mean, before I knew anything about it, and I'm hearing, scientists are experimenting with neural networks and neurons, and of course immediately we think of biology.
For sure.
And I'm thinking, this sounds a bit like Frankenstein. Is this sort of a brain in a jar type concept?
It's interesting, a lot of the AI pioneers had a biology background or a...
Absolutely. And I think, if I'm correct, some of this sort of stuff was actually invented by people looking at very simple things like insects' eyes, and insects have quite simple eyes, and the connections between their retinas and their optic, the optics, and that gave people the idea of, can we get anywhere with this? But for the data scientist, a neuron is nothing more than a simple calculation, and that calculation typically has a number of inputs, could be a small number, 2 or 3, it's often 1,000, 10,000 inputs. And it does a calculation and it gives an output. And going back to your very first question, that calculation is trivial. It basically takes all of the numbers that come in, multiplies them by another number, and then it optionally can add or subtract a constant. And that's it. That's what it does. So when we're building a neuron in a computer, we're writing a piece of code that just takes input numbers, multiplies them by these weights, they're called. You add it all up, and then you might add a constant adjustment, plus or minus at the end. That gives you your answer. So it's that simplistic calculation is the neuron.
And how does that work within something like going from the 40s to the 50s, like the Perceptron machine, in terms of the work of Rosenblatt and what that was?
Yeah, I'm keen on the perceptrons because I'm kind of old-fashioned. I mean, at home, most of my stereos that I listen to are valve radios, valve stereos. I love the old-fashioned sets that take a long time to warm up, and of course those were the days when stereos and radios would all have been built around valves, and the first computers as well. So I'm very keen on all of that kind of stuff. Before the digital computer, there was a concept of an analog computer. And there's so many things that electric circuits that can model, in a way, the world. So there's an electronic component called a capacitor, and it holds charge. And if you apply a voltage, it will charge up. But it'll charge up quite quickly at first, and as it gets full, it slows down the charge. So if you were to graph the charge on a capacitor, it's modeling a nice curve. Well, that curve could actually help you to model something in the real world. And if you place a resistor over that capacitor, it would start to decharge and discharge, and how quickly. And so just putting together electronic components, people built models where the model output wasn't like our computers, an image or a set of numbers. It was an electric voltage that was giving the answer. And they first started building what was called the perceptron, which was to try and get behind some of these ideas of neurons and insects and eyesight and image recognition. And they did it by making circuits, physical circuits. And you know, like on your stereo, you have the volume control. A small signal comes in and you can crank it up and you get a really loud thing. And then, of course, you know, the wife will probably come and say, look, turn that down. Small signal comes in.
Likely.
Likely. Be careful. Tiff will be watching this. And, you know, it does. So there's this concept of different sort of amplifications. And what they did to build their sort of connection of neurons was have lots and lots of dials that you could adjust, and lots of inputs, which actually came from a camera, a very early sort of idea of a digital camera. And yeah, that would allow them to sort of experiment with all of these things. But of course it was really big and clunky. And if they ever wanted to try a completely different approach, they'd have to order all the parts and solder it all together, and it was terribly slow, terribly labour intensive.
Difficult to adjust the weights.
Absolutely. But they did make incredible inroads. And I think they understood where this could lead, because there are some examples in newspaper cuttings and things from back there, this was so late 40s, 50s, of, you know, people saying, this could be the basis of a machine that actually thinks.
Sure.
But I think people were quite horrified by that idea.
Absolutely. And I think also, like, it's a good historical example, perhaps, of the invention not necessarily being at the right time, perhaps 60 years too early in the sense of the limited compute resources, to your point, literally like building these things together. I think when Rosenblatt experimented with it, it was on an IBM 704, so not exactly, that would probably take up this entire room.
Yeah.
So not exactly supercomputing, but perhaps some of that hype from a newspaper perspective and all the clippings, is this the first machine that can have an original idea, sort of disappointed when it was really just trying to recognize, is this A or B from a letter perspective in terms of the actual application, but how it got there was sort of the magic, to your point.
Yeah.
And I think there was a book in the late 60s called Perceptrons from Marvin Minsky, and it talked about sort of the criticism of them, and it took a really, really long time. It sort of ushered in this first AI winter, and it took a while for that to ultimately thaw. But it's interesting, your discussion of the stereo analogy and the weights and adjusting those, because I think the original Perceptron was an idea of like a single layer neural network. You would know this much better than me. But sort of when that winter thawed from an AI winter perspective, I think part of the catalyst was some work that Geoffrey Hinton and David Rumelhart were doing around backpropagation and trying to get neural networks to work with multiple layers. What was so important about backpropagation in terms of it sort of ushering in this rejuvenation of interest in machine learning? Like, how did it ultimately function? Especially, you know, the weights example is brilliant.
When you take the decision to move away from your two-dimensional vector to, let's say, a 10,000 dimensional vector, you've given yourself a bit of a practical problem in that there's just an awful lot of numbers that you're dealing with. And when you then put in another layer of, say, 10,000 items, and perhaps another layer, and they're all connected to each other, suddenly 10,000 becomes 100 million, becomes just the numbers of
exponential.
Crazy. And we often hear that these large language models might have billions of parameters that needed to be trained. And what you're doing in a model was called sort of forward propagation. And it's quite easy, like a funnel. You put your 10,000 numbers in the middle, in the top, and it all goes through this funnel, and what comes out is a number. So an early example was handwriting recognition. So let's imagine we took a photograph and they were very grainy, so they would probably only have something like, it might only be 10 pixels by 10 pixels. So a very grainy sort of picture of let's say a letter A. But you've got 100 numbers there, the intensity of each pixel. You throw all that into your funnel, and the funnel distills it all down, and let's say it will have 10 outputs. So the example of recognizing the digits 0 to 9. And each output, you want, if you show it a 1, you want the output 1 to be positive in some way, and all the other outputs to be a low number. You want to see a differentiation. You show it a 7, you want the 7. So it's quite easy when you get an answer, you've only got 10 numbers, and you know what you want. So you can see where it's wrong, because you're only looking at 10 numbers. But the problem of then training is, well, I know what answer it gave me, and I know what answer I want, so I know what I need to adjust. And I've only got 10 outputs, so I only need to adjust 10 things. But then which of the thousands of weights do I need to tweak to get what I want? And to a human, that seemed seemingly impossible. But the concept of backpropagation came when I think folks realized that each weight actually has a kind of a concept of sensitivity. And again, this comes back, Newton would have loved this, because the concept is the slope of a curve. You could have a curve on a mathematical curve, and it might have a zero slope, with the flat bit at the top, or it might have a steep slope, a steep negative slope, steep positive slope. And that's the idea of, it's a bit like on our stereo example, a volume control that if you tweak it a tiny bit and there's a sudden change in volume, it's a sensitive control. Or you might have a control that's not sensitive. And what people realized was that the sensitivity, I'll stop calling it that, it's the slope, is vital. And when you've got your 10 numbers at the end and you know there's an error, and you think, well, what do I go back and adjust and all these things? The answer is staring you in the face. It's how sensitive are those? And adjust them in proportion with that sensitivity. And this was all kind of proved mathematically using, again, things that Newton just loved. Because the concept of slope actually comes from, sorry, this sounds horrible, but differential calculus. It's the derivative measures the slope of a curve. And there was a concept that goes back hundreds and hundreds of years, which is if you've got compound functions and you know the slope of, let's say we do a function and then we take the answer and we do another function. If you know the slope of each of those two functions, you can very quickly derive the slope of the compound. So it's a way of joining together functions. And they said, well, wait a minute. These layers in this neural network, they join together in exactly the same way. And so we apply this technique of getting the derivative, the slope of compound functions. It's just compound layers. And there was the answer. And I will be doing this actually on a explainer video. I want to, there's a lot of confusion about how backpropagation works, and I want to derive the backpropagation and explain it in depth, which is something I'm going to come on to hopefully do on a future video. But that cracked the answer.
Absolutely, that's brilliant. Love it. Moving from neural networks and backpropagation ahead a little bit, sort of current times, or at least within the last decade, wanted to ask you about transformer models and the attention is all you need paper, and really what the breakthrough was from that perspective in terms of fueling this sort of generative AI age that we're in today. Like, why was that paper by Google so important for all the technology we have available now?
It took me a while to sort of get behind the ideas. In general, a lot of these papers, they summarize quite groundbreaking ideas in very condensed math that it looks simple, but you don't really understand what's going on. And I had to sort of read it through many times before I started to get, and I'm no expert on transformers, but light bulb moments. And it was because I suddenly saw things and I think, wait a minute, I've seen this idea before. This is something that was done in whatever it might be. And transformers look terrifically complex, but again, they're basically simple math of necessity, because the backpropagation algorithm is needed to train something. So you can't really invent something that gets away from this idea of taking an output, measuring how wrong it is, and then going back and correcting your parameters. That's the basic idea. So the ideas we've talked about, these vectors and things, they all still stand. But transformers did some brilliant things. And so one of the first things was this idea of optical character recognition. You show it a character and it can say, okay, that's an A, or that's a Z, that's a K, and it can look at it. Language is horrible from a computer's point of view, something that humans have invented to be so complex, obtuse, difficult. We can all invent sentences where there are two words, one at the beginning. Okay, let's have a little game here. Let's play with one. So, Rab.
Yes.
You crazy boy. Whatever you do, please don't open the back door. Go to the back shed and look in the cupboard and drink the poison. I'm just giving like lots of words that really don't mean anything. But what I wanted to tell you was don't drink the poison.
Drink the wine.
Drink the wine instead, yeah. So, well, if it's my garden shed, there might be some wine hidden down there. There might not, so in case my husband is watching. But yeah, you know, I was just bulking that out with lots of description. But the key words were the first one, don't, and the last one, poison.
And that's what I paid attention to.
But you got that.
Yeah.
A computer can't do that because
Right.
there's a time element. So for vision, we look at a picture and we see, and we can make an observation without the time element. When we're getting words, the computer's going to, yeah, come on, what are you saying? Yeah, yeah. And I love it. I love using things like Google Translate now. And sometimes you're typing in a word and you notice it goes back and corrects things that it might have translated because it thinks you're going along a certain path, and then you're putting a word and it says he's actually got a different meaning, and it goes back and corrects things that it's done in adjusts because the time element is important. And Transformers did that brilliantly. They came up with an idea of how to tackle exactly that problem.
And allow the machine, in a sense, to pay attention to what matters.
Attention was the word, wasn't it? And again, and I love it because it all comes back to vectors. You know, we talked about vectors having this concept of direction. And when we talked about embedding, we talked about that cat and dog will have a similar direction.
For sure.
And all the transformer does, and it's so simple. If you take a sentence and you write the words along, say, the top of a piece of paper, and you write them down, vertically in the column, you can produce a little grid, and you can calculate what is the sort of the difference in direction, which is just a single number between each of these things, and you get like a heat map. And in that grid, you might have, and I have no idea if this would be the case, but the don't and poison might be, have very high numbers. And so words that really aren't connected with each other will have low numbers. And that just comes from the embeddings. But that calculation was done in transformers, and that forms one of the inputs. So the transformer gets the words as embeddings, of course, so it just gets those numbers. But it gets that little map of interconnectivity between so where's the importance, where's the semantics? Very simple. So all they did was a calculation of the direction of the vector, but they'd given the algorithm, the model, really interesting, important semantic information. And that was genius. And then the other one that I absolutely loved was they decided to give the model a hint as to where the words were. And they said, well, what if we could give it the information that this is word 1, this is word 2, this is word 3, this is word... But they were so clever, they probably experimented with giving a separate input. But those inputs, how do you connect them to the words? And what they actually did was took the vector for a word, which is, remember, just a list of numbered, and they create another vector, which means position 1, or position 10, or position 20. And they just add those vectors together. And that position marker behaves a bit like a watermark. So you can see the word behind, but it's got this position superimposed. And I loved that idea, the idea of a watermark. And I'm sure when they were experimenting with these things, they probably thought, well, we've got no idea whether the computer's going to be able to use that information and learn. But the fact that computers can learn, this is a cat, this is a dog, they do amazing things. They thought, well, why don't we just throw this watermark in and just see if that helps the transformer to make sense of languages. And guess what? It worked. It worked brilliantly. But the other thing, you talk about history of numbers, and I loved this about that watermark that they put in. They calculated it using a sine curve. A sine curve is actually what comes out of the power socket. electricity forms a sine curve because it comes from anything that rotates. And you see sine curves in everything. So, from electricity transmission, you think of a radar at an airport, the aerial is rotating. Mm-hmm. There's a sine curve around that. If your early navigation systems in aeroplanes, airports actually transmit two sine curves. Mm-hmm. One has a fixed phase, and the other has antennas that point in different directions, and they transmit a slightly different sine curve. And modern, even today, aircraft still do this, but this technology has probably been around since the 50s or 60s. You can receive these sine curves, measure the phase difference, and that tells you the angle you are from the airport. That's how aeroplanes used to navigate before GPS was invented. So there was an example. Aircraft navigation, sine curves told the aeroplanes where they were in connection to an airport. What did they do with the transformers? They said, we're going to chuck a sine curve in and put it on these words. It'll tell you where the words are in relation to the start of the sentence. And when that light bulb came into my head, I thought, they're using something that dates back, that's been known about for
sure.
But it was brilliant, genius, that people thought, let's try that. And it worked.
Seems that there's quite a link between direction and geometry to machine learning. And there's a great quote in this book that I'm reading called Genius Makers from Hinton, again, one of the godfathers, I guess, of modern AI and whatnot, and one of the people behind the Transformer paper, I believe. But he talks about what's old is new in terms of ideas. It's just the application, figuring things out once you have more computing resources or new discoveries are made. But speaking of computing power and transformers, I would be remiss if we did not talk about on January 30th what's sort of going on in the AI world today. Because last week you have Project Stargate announced, where we're talking about $500 billion of investment into the US to build data centers. And then this week, speaking of transformers, what do we have? DeepSeek, which flipped everything on its head in terms of the stock market. Literally $600 billion in NVIDIA stock value lost like that. And it's sort of, the juxtaposition of the two events kind of prompted an interesting question that I want to get your thoughts on around the theme of one week is we need more compute, more infrastructure, more data centers, more powerful chips. The theme of the other week with DeepSeek is, well, maybe we don't actually need that. Maybe there's algorithmic ways to figure out how to get more utilization out of GPUs that they had, or the less amount of budget that they have to actually build that model that's competing with some of the best from Google or OpenAI. Is the magic in the math from an algorithmic perspective? Is the magic in the machine from a compute perspective? Or is it really not that binary and a product of both?
Both have an important role to play. Actually, you telling me that it made me laugh because some years ago I did a little game with some of the folks here at JTA, and I said, I'll give a prize to the person who can write the fastest piece of code. And it was to actually calculate something that actually Isaac Newton was involved in. I would have known about, called the Taylor-Maclaurin expansion. And I asked them to compute it to a ridiculous degree, 10,000. And I think most people were very close. They were getting run times of about 30 seconds, 29.9, and there was all this rivalry going on in the office, and I was just laughing.
Bit of banter.
And actually, my lovely sister-in-law won the prize and got the prize. She managed to get the most performant code. And then I showed them my code that did it in 0.3 of a second. And they're like, wait, no, what, how? And I can't take the credit for that. We had a very ancient transistor computer at my school called an Elliott 903. It was a wonderful thing. I absolutely adored it. And I was interested in how it did calculations of things like square roots and sines and things, because I'm a geek, right? So I looked through the code and I saw, wow, that's a really clever programming technique to shave off time. And always remembered that. And that's what I used on this example. And none of my team clicked on that amazing technique. So there's always examples where suddenly someone has a moment and says, I can do this much more quickly. And that's, of course, what's happened. And I mean, it really is tragic what's happened to NVIDIA's stock price. I mean, that shores up pensions, and it's important to people.
I'm sure they'll be okay.
And
it seems to be rallying back.
It seems to be rallying. Well, that's the point. And what China have done is, and they've been absolutely amazing, by open sourcing this now, people are downloading it, and it's so accessible. I've seen YouTube videos already, it's only been days, people are saying, I can run this on a Raspberry Pi, I can run this on my laptop, So it's so accessible to everybody. And of course, that's going to help fuel invention.
Absolutely.
And like we were talking about, Newton was doing two-dimensional vectors, and he could look at, say, planetary motion. But now, with a 10,000 dimensional vector, you can start to recreate intelligence. It's a huge leap that no one could have foreseen. What if we take this new ideas that's so much more efficient and so much quicker, but we actually unleash all of that massive computing power that we're now saying is no longer needed. But wait, what if we unleash that on that more efficient algorithm? What it means is that we'll be able to train models that were just simply out of the current scope. And what if that means that we actually we're expecting artificial intelligence to sort of, will it come up to human levels? Will general intelligence exist?
Yeah, AGI.
What if we get a kind of intelligence that is massively, massively better than our intelligence in ways that we just cannot perceive? Maybe that will happen.
Absolutely.
And then it'll be NVIDIA's chips.
No
and
doubt.
Other companies, I should say.
Absolutely.
That build these kind of chips. It'll be those kind of a marriage of those technologies.
For
so
sure.
I'm not. I mean, this is stock markets. They get the jitters. They
They're sensitive.
but it's all good. We've got some incredible technology being
sure.
built by these American companies that tremendously powerful. And now we've got, incredibly skilled mathematicians in China who've come up with, it's all good, it's a win-win.
Absolutely.
And we've got to take out we've got to use this for humanity. It's not about who keeps the code, who keeps the IP, who makes the money. I understand that's very important, it needs to be done, but what's actually happening is a democratization
Of intelligence, really.
I think that will be ultimately. There are risks around AI. Let's leave that for another day. But
Absolutely. But I love your example
good.
of what about that, people saying that compute's useless now. Well, actually it's not. I think
Not at all.
right after, and it sort of strikes a similar tone to what you just said, this whole DeepSeek fiasco came out. Satya Nadella of Microsoft said, Jevons Paradox Strikes again, which is this notion that the improvement of a product or resource in terms of its efficiency will actually drive consumption, not reduce it. So definitely on the same wavelength there, but we'll save AGI for another video. But this was an absolute pleasure, super interesting. I learned a lot, felt like I was back in math class, but it's really amazing, this whole notion of, again, what's old is new, and how consistent these mathematical concepts and capabilities really are throughout this through line of the history of machine learning and how it'll continue. So thank you.
I thank you.